Hello, today we're going to talk about backpropagation, the main training algorithm used for neural networks now. Backpropagation was actually introduced in the 1970s, but it was unappreciated until a 1986 paper from Rummel Hart Hinton and Ron Williams described that it works much more efficiently than most other neural network approaches. Today, backpropagation is basically the workhorse of the entire field of deep learning. Before we understand backpropagation, we have to understand forward propagation. Forward propagation is basically how a neural network propagates signals and computes output. Forward propagation is actually quite simple. Basically, if you want to figure out the activation of the jth neuron in the nth layer, what you have to do is you have to get all of the activations coming from the previous layer and take their weighted sum with the weights on these edges. So here we have 3 edges coming into this neuron here from the 3 previous neurons in layer 1. And then to that, you add a customized bias for this particular neuron at this layer. And you take this whole weighted sum and you transform it by the activation function, which is a nonlinear function, like the sigmoidal function. And this gives you the activation or the output value that this neuron outputs for the subsequent layers. So if you just repeated this equation for every neuron in the neural network, layer by layer, then you'll have the computation of the output of the neural network. Of course, if you have an input neuron, then these activations are replaced by the inputs. In order to simplify the way that the forward propagation looks, we can turn some of these into matrix operations. Here, W, L is all the weights coming into this layer, and these are all the activations from the previous layer, and we turned this into matrix vector multiplication, and you added a vector to it. Another way you can simplify the notation is by adding this intermediate quantity that just computes the sum before transformation by the nonlinearity. And Z is often used for this intermediate sum, which we will encounter a little bit later also. Now the goal of backpropagation is to compute the partial derivatives of every weight and every bias in the neural network with respect to the cost function. The cost function is, of course, a function that compares the desired output of the neural network with the output that the neural network is actually giving right now as part of the activations of the final or the capital Lth layer. Here we see that we have an example of the quadratic or the mean squared error cost, where for every training example, you're taking the desired output minus the neural network output and squaring it and then taking an average. This is a common feature of cost functions, that they can be written as a sum over the costs of every training example. So in summary, the reason we can actually theoretically derive the partial derivative of every weight and bias with respect to the cost function is because the neural network output and the cost function itself can be written as a function of the weights and biases, and the cost can be written as the average cost over a batch of training samples. So let's think about how to derive these partial derivatives for a second. So suppose you wanted the partial derivative of this weight right here. Then think about what happens when you change this weight by a small amount delta. Okay, so this weight is going into this neuron, so it changes the activation of this neuron by some amount delta. And in the next step, that activation cascades its change to all of the neurons in the next layer, and so forth until it gets to the output. So this suggests that if we could track how the weight change propagates, then we could compute the gradient. Let's try and see what we come up with. So any change causes change in the weight causes a change in the following activation. So this is the change in the activation with respect to change in the weight times the change in the weight. Now, in the next layer, it's causing a change in the next layer's activation, which is actually passing through every neuron in the next layer. So this is giving you a bunch of paths. And in the subsequent layers, You're just basically summing over all the paths. But now we can see here that we're basically referring to derivatives of activations that are computed in the subsequent layers. So what if we had computed all of this backwards, like we'd computed all of these terms to begin with? Then we could simply, add on this one particular derivative here and be done with it. And that's basically the idea of backpropagation. So first, before explaining actually what backpropagation is, let's introduce an intermediate quantity called error at the node. Error at the node is error at the input of the node before the nonlinear activation. So basically error in those z terms. Okay, the delta error at the jth node of the lth layer is the error coming into the jth neuron in the lth layer. This enables us to relate this error back to both the weight and the bias in one step. So if you think about it, a change in this error results in a change in the cost. Either the error is large, in which case it's large positive or large negative, and this little demon here can lower the cost by choosing to alter this z value in the opposite sign of delta, or it's close to 0 and you can't decrease the cost much by perturbing this value at all. So let's see how we come up with that logic here. By definition, the error at the output node is the partial derivative of the cost function with respect to this weighted sum coming into the last layer's node. You basically have to use the chain rule to get the idea that this is the derivative of the cost function with respect to the activation, which is out here, and then the activation with respect to the weighted sum coming into the input. And so if you recall that the activation is just this sigmoid or whatever nonlinear activation applied on top of the weighted sum, then you get that the error at the node is the derivative of the cost function with respect to the activation, and then the derivative of the sigmoid or the activation with respect to the weighted sum. That is the so-called first equation of backpropagation. The second equation is the error at some other node, which is the error in the jth node in the lth layer, or the jth neuron in the lth layer. You can rewrite this delta in terms of the delta errors of the subsequent layer. So delta of the lth layer is equal to the sum of the derivative of the z of the L plus 1th layer with respect to derivative of the z of the lth layer times the error that you've already computed at the L plus 1th layer. Differentiating this gives you this quantity where you have the weight of the L plus 1th layer times the derivative of the activation function in terms of the input coming in, and then you get a formula that looks like this, which sums over all of the weights in the next layer with respect to the activations in the present layer. The third equation is the error of a bias function. You can just see that if you have the error of the z, then you can just tag on the error of the bias by differentiating z with respect to the bias using the chain rule. And so you see that the derivative of the bias with respect to the z is just 1 because the bias is a constant. So the derivative of any bias with respect to the cost function is just the error at the node. The derivative of the weight can similarly be found by cascading this value with this one. But here we no longer have a constant value, and instead we have the activations at the L minus 1th layer. So this gives us that the derivative of the weight at the nth layer is the error in the nth layer times the activation from the previous layer. So this gives you the 4 fundamental equations of backpropagation. This is the error at the very output layer, going into the output layer. This is the error of coming into any other node, and this is how you relate the error coming into the node to the bias, and this is how you relate to the error coming into the node to the weight. And here we've taken another notational simplification with the element-wise dot product here. So what insights can we gain from the 4 fundamental equations? Consider the output layer. If you take the output layer of the sigmoidal function, you see that this activation becomes very flat when the activation is close to 0 or close to 1, and the derivative is close to 0. The weight in the final layer will learn slowly if the output neuron is so-called saturated, i.e. it's very close to 0 or very close to 1. Other insights for similar insights for other layers is that the weights will learn slowly if either the input neuron is low activation or the output neuron has saturated. The 4 fundamental equations hold for any activation functions. We can use these equations to design activation functions, i.e. we can choose activation functions that are always positive and never close to 0, such as the rel-u activation we'll see shortly. And understanding the 4 fundamental equations can sort of guide us in designing the neural networks, even though a lot of people view them as a black box. So putting it all together, how can we let the neural network learn by propagating these errors backwards? Basically, you take a set of training examples. For each of the training examples, you set the input activation and you compute the forward propagation or feed forward. Then you compute the error at the output, backpropagate the error to every other layer to compute the error at those nodes, and then you relate them to every weight and bias. Now, what does gradient descent do? Gradient descent takes this gradient and moves in the opposite direction so as to lower the cost. And this is done with respect to a learning rate here called nu. So each weight is updated by whatever the weight is plus a step in the direction of the gradient, and each bias is also updated by a step in the direction of the bias. And this learning rate is a parameter that's often very carefully tuned or even scheduled. So this gives you in a nutshell how neural networks are trained. Neural networks are basically trained by finding the gradient of every weight and every error, every bias in the neural network, and stepping in the opposite direction of the gradient by a factor of nu.